Modern residential infrastructure operates on systems that maintain baseline energy consumption regardless of occupant behavior. Refrigeration cycles run continuously to preserve food safety. Water heaters maintain temperature reservoirs throughout the day. HVAC systems respond to thermal loss through building envelopes. These loads exist as a function of the infrastructure itself rather than discretionary use patterns. Data from residential energy audits consistently shows that approximately 60 to 70% of household electricity consumption occurs through systems that cannot be deactivated without compromising basic habitability or safety standards. The refrigerator-freezer unit alone accounts for 13 to 15% of typical household consumption, operating on automated compressor cycles independent of human intervention. Water heating represents another 14 to 18%, with standby heat loss occurring continuously even when no hot water is being drawn. Climate control systems demonstrate similar structural consumption patterns. A home maintains thermal equilibrium with its external environment through insulation barriers, window seals, and air exchange rates that were determined at the time of construction. HVAC systems compensate for this thermal transfer continuously during heating and cooling seasons. Adjusting thermostat settings reduces but does not eliminate this compensatory load. The physics of heat transfer persist regardless of occupant preferences. This creates a consumption floor that exists prior to any behavioral choices. Before a household makes a single discretionary decision about lighting, entertainment systems, or appliance use, the structural systems have already established a baseline load that will consume the majority of monthly electricity. I'm James Sullivan. Let's look at how people typically try to manage this problem. Households attempting to reduce energy costs typically begin with behavioral modifications focused on discretionary consumption. Lights are switched off when rooms are unoccupied. Thermostats are adjusted to less comfortable temperatures, higher in summer, lower in winter. Appliances like dishwashers and washing machines are operated during off-peak hours when time-of-use rates are lower. These adjustments require continuous cognitive attention. Each interaction with a light switch, thermostat, or appliance becomes a decision point where cost considerations compete with comfort or convenience. A household might establish rules. No air conditioning until outdoor temperature exceeds 85 degrees, heat maintained at 65 degrees maximum in winter, television and electronics fully powered down rather than left in standby mode. Another common approach involves usage scheduling and load management. Laundry is consolidated into fewer cycles. Showers are shortened and timed. Cooking methods shift toward appliances with lower energy consumption. Microwave instead of oven. Toaster oven instead of full-range burners. Some households adopt phantom load elimination practices, unplugging chargers and small appliances when not actively in use. A third pattern involves the pursuit of technological efficiency through appliance replacement. LED bulbs replace incandescent lighting. Energy Star certified refrigerators replace older units. Programmable thermostats introduce automated setback schedules to reduce heating and cooling during unoccupied hours. These upgrades represent one-time interventions that lower the consumption rate of specific systems. Each of these approaches operates within the constraint of existing infrastructure. The behavioral modifications address discretionary load. The efficiency upgrades reduce the consumption rate of baseline systems. Neither approach restructures the fundamental relationship between household and grid-delivered electricity. Behavioral conservation measures demonstrate measurable decay in effectiveness over time. Initial reductions typically range between 8 to 15% of total household consumption, but sustained adherence proves difficult. The cognitive load of continuous decision-making competes with other household priorities. Comfort standards that were temporarily adjusted become sources of persistent low-grade stress. Temperature-related savings illustrate this pattern clearly. A thermostat setting of 68 degrees instead of 72 in winter represents a 5 to 6% reduction in heating load under typical conditions. This difference is tolerable during moderate weather but becomes acute during temperature extremes. When outdoor temperatures drop to 20 degrees or below, the indoor experience at 68 degrees shifts from slightly cool to persistently uncomfortable. Households often abandon the lower setting during the coldest portions of winter, precisely when heating costs are highest. Phantom load elimination and usage. Scheduling face similar sustainability challenges. The effort required to unplug multiple devices after each use or to coordinate laundry and dishwashing with off-peak rate windows accumulates as routine friction. These practices demand ongoing attention that conflicts with normal household rhythms. Evening hours when families are home and most active are also peak rate periods when usage should theoretically be minimized. Efficiency upgrades encounter a different limitation. They are self-exhausting interventions. Once a household has replaced incandescent bulbs with LEDs and upgraded to Energy Star appliances, no further reduction pathway exists within that category. The consumption floor has been lowered, but it remains a floor. A refrigerator drawing 400 kilowatt hours annually instead of 600 is more efficient, but it still draws 400 kilowatt hours annually regardless of occupant behavior. The fundamental constraint is that all these approaches assume the household will continue to draw electricity from the grid at rates and on terms determined externally. Conservation reduces the volume of that draw, but does not alter the structural dependency or the price-setting mechanisms that operate independently of household consumption levels. Outside the conservation and efficiency framework exists a category of approaches that involve establishing generation capacity at the household level. These formats shift the structural relationship from exclusive consumption of externally delivered electricity to partial or complete on-site production. This category encompasses various technical configurations: solar photovoltaic arrays with battery storage systems, small-scale wind turbines where geography and regulations permit, micro-hydroelectric installations in properties with water flow, and mechanical or electromagnetic generation devices occupy this space. The defining characteristic is that electricity production occurs at the point of use rather than through centralized utility generation and distribution. These formats operate on different economic structures than grid consumption. Rather than ongoing variable costs determined by kilowatt-hour rates and usage volumes, the household incurs front-loaded capital expenditure for equipment installation, followed by maintenance costs that are generally more predictable and lower than cumulative utility payments over the same time frame. The format category includes significant variation in scale, complexity, and interaction requirements. Some systems maintain grid connection for supplemental power or net metering arrangements. Others operate as isolated microgrids independent of utility infrastructure. Installation complexity ranges from professional contractor requirements to standardized procedures accessible to non-specialists with technical documentation. Component costs for many of these formats have decreased substantially over the past 2 decades, while efficiency and reliability have improved. What previously required specialized engineering knowledge has, in certain format types, become implementable through widely available materials and documented assembly procedures. One format within this category involves compact electromagnetic devices designed to amplify electrical current from low-voltage source inputs. These units typically consist of precision wound coil assemblies in specific geometric configurations, housed in weather-resistant enclosures sized comparably to a medium portable generator. Installation generally involves positioning the device in a utility area, basement, garage, or protected outdoor space, and connecting it to a small-scale input source, such as a solar panel array, battery bank, or parasitic draw from existing circuits. Output routing connects to household electrical panels through standard wiring protocols. The devices operate continuously once installed, requiring no activation sequence or operational management during normal use. Maintenance typically consists of periodic inspection of electrical connections and housing integrity rather than consumable replacement or mechanical servicing. The coil-based design contains no moving parts subject to wear beyond electromagnetic field generation. This format represents one configuration among multiple approaches to household-level electrical generation. Its appropriateness depends on factors including local electrical codes, existing infrastructure compatibility, available input sources, and household technical capacity for installation and basic maintenance. The underlying dynamic that modern residential infrastructure creates baseline consumption loads resistant to behavioral modification operates at the level of building systems and appliance design standards that developed over decades of grid-centric electrification. Individual household responses occur within these structural parameters. Alternative format categories exist in the market, reflecting sustained interest in options that restructure the household-utility relationship rather than optimize consumption within existing dependencies. The effectiveness of any particular format for a specific household depends on variables beyond the scope of this analysis. Behavioral conservation and efficiency upgrades remain the most common response patterns to rising electricity costs, constrained by the mechanical and thermal realities of residential infrastructure that establish consumption floors independent of occupant discipline or awareness.